Welcome to what may be your first famous Francois video. Today we're going to be talking about curved, also known as spherical, mirror ray diagrams and how to make them. So let's jump right into it. So your initial setup of this is that, of course, you're going to need your curved mirror. You can flip this around, make it into either a concave, as you can see it there, or convex, which would be an opposite direction. Along this, down the center of your mirror is the center, also known as the optical axis, if you see it in another location. Then you have your focal point, which is some distance out from the curvature. It's always towards the center of the curvature. So since this is the curvature right here, you've got a line that goes in towards it, right? Basically think of it as sitting inside the bowl. And a good way of finding this focal point is actually finding the center of curvature first, which is, since our curved mirror, the reason why it's called a spherical mirror is because if you continued it all the way around, it would form a perfect sphere. And the center of curvature is the center of that circle, so the focal point is half of that distance, exactly. And then the last thing that we need for our setup is, of course, our object that we want to reflect off of this mirror. And some objects are represented by arrows, sometimes you do them as stick figures, doesn't matter which. What we do need, though, is just something to represent it. So I'm going to use an arrow here. Now, the rules for our ray diagrams, we'll take them through one by one. A ray that is in line with the focus point, which strikes the curved mirror, will reflect off in a direction that is parallel to the center axis. So let's see what this kind of looks like. So we've got our object, our initial setup right here. So we'll take this example first. And we've got our ray, so it's going through the focal point. So it's definitely in line with the focal point. When it hits the mirror, because of the geometry of it, it will actually bounce back off completely parallel to that center axis. Okay? But what about if our object is in front of that focal point? We can't draw a line through it to the mirror, so let's take a look at what happens with that. So we've got our object here. What we do is we create a line, you can see it there as the dashed blue line, to the object. That's not actually where our ray goes. This is just our line to line up with the object, because it has to be in line with the focus. It doesn't have to go through the focus. So we create a ray in the same direction as that line. When it hits the mirror, it will bounce off parallel to the center line. Well, that's for concave mirrors. What about our convex mirror? Well, with a convex mirror, it looks something like this. We've got our object on the left side. We've got our curved mirror in the center. The focus point for a convex mirror is on the other side of the mirror this time. And so we draw a line through it to know where it's going to line up, but we stop our ray at the mirror because, of course, our ray does not actually go through the mirror. Light doesn't go through the mirrors, right? It reflects off of them. So we draw it there, and then it reflects off parallel. So it doesn't matter which type of curved mirror you're using. It only matters what you're drawing towards. So it's always being drawn towards this focal point here. Our second rule is that a ray that is parallel to the center axis, which strikes a curved mirror, will reflect off in a direction that is in line with the focus point. So it's basically the exact opposite of what we just did. So if we draw a line that is parallel from the top of our object to the mirror, it will bounce off through the focal point. Not that bad, right? So what about when it's over here? Well, we draw it parallel, right? And then it bounces off through the focal point. Basically the same as last time. But what about the convex mirror, like this? We can do a parallel one, but now we can't draw through the focal point. So just like what we did last time with the last rule that we just did, we will draw a line in line with the focus point from where it hits the mirror, and it will go off that way. Pretty easy, right? Not too bad. So what about next? Well, this next one is there is an optional third one that you can do. 2 is all that you really need, but we're going to see that the third one will also create a easier way of looking at this. So a ray that is in line with the center of curvature, which strikes a curved mirror, will reflect in the exact opposite direction. So this ray is on the normal line from the mirror. We remember this from our law of reflection. Law of reflection states that when a ray comes in to a mirror, whichever way is perpendicular to the surface of that mirror, that's what we call the normal line, and it bounces off with the same angle that it made with that, just on the opposite side. So if it came in with a 15-degree angle, it goes back off with a 15-degree angle. And since our center of curvature actually lines up exactly with the normal for where we're going to strike the mirror, it will bounce exactly straight back. 0 degrees equals 0 degrees. So we can create this third one with a green line here, comes in, hits that, and then bounces back. And you can see that all of our reflected rays are crossing here. That's going to be important in a second. But let's go to the other diagram. We can make another one. So if we line up a ray with the top of our object hitting the mirror and the center of curvature, it bounces straight back, just like the last one. And in our new one here, we create a line up with the center of curvature. It's not going all the way to the center of curvature because that's inside the mirror and we don't want that. But it hits it and then it bounces back again. So, showing the image. So the image shows up. Why do we do the ray diagram in the first place? Well, we want to show the image. The image occurs where 2 or 3 of your reflected rays intersect. I say 3 because you can have that optional third one. If they do not intersect but are not parallel, then you must extend the reflected ray's origin point into the virtual world, and we'll see what that looks like in a second. So let's go to our first ray diagram, the concave mirror. When your object is far away, we can see that all 3 of our lines are lining up right here. So when we put our image, it's there, it extends to the center line, just like our original object does. And so we end up with a flipped version or inverted image. And since it is over here, it is called a real image. Okay, if it is real if it is on the same side as the object. That's because we could put a little screen right here. You may have done this with, say, an index card and a small concave mirror, like a compact mirror. And you can see an image of an object if it's giving off enough light. So if you have a little light bulb like you may have in class, you could see the image of the light bulb reflected at this image point. This is a focused image. Okay, anywhere else, if we were to put our screen right here before it or right here after it, we would have a blurry image because the light rays coming off of the same point aren't converging at one point, and so you get a distributing effect of the light across an area. If we look at what happens when we have a ray diagram when we have a concave mirror and our object is closer to the mirror than the focal point, then we can't connect these ones, right? They aren't parallel, but they aren't coming together into that single point like it was in the last one. So when we look at this, we have to trace back the line. So what we have to do is we have to move our diagram over. And what we can do now that we've done that is we can trace back these reflected lines, only the reflected lines being this yellow one, the green one, and the red one. You don't need all 3 again, all you need is 2, but you can see that they all meet up at the same point over here. And so you actually get an image over here, and this is upright. It is magnified, as you can see, but since this image isn't actually coming from a single source, this is actually not where the rays converge, right? This is just we're tracing back where they would converge. It is not real, it is virtual. So this is our virtual upright magnified image. This is why we use a beauty mirror, because we want to see our lovely face in the mirror, okay? And we want to see an up-close version of it. So we don't want to project an image of our face onto a screen. What we want to see is an image in the mirror that is magnified so that we could use it. With a convex mirror, we have to, again, trace our reflected rays only, which is, again, the red, the green, and the yellow ones depicted here. And we find that they come together over here. Again, it is virtual. It is upright, but this time it is reduced. And this happens with any object at any distance in a convex mirror. It ends up being much, much smaller. So that is your lesson for drawing ray diagrams. I hope you will join me again on another one of Francois's fabulous physics adventures. I will see you next time or in class.